All right, well, welcome everyone to our July 2021 indoor meeting. Please be respectful, mute your microphones during our presentation. Our presentation today is from Monti. It's called the Grand Tack Hypothesis, the Great Migration of Jupiter and Saturn in the Early Solar System. So Ron is a science instructor for the NC State's Osher Lifelong Learning Institute, a volunteer educator and exhibitor at the NC Museum of Natural Sciences, and an outreach speaker for the Raleigh Astronomy Club. The summary he gave us for his lecture is that based on recent discoveries about exoplanetary systems and highly sophisticated computer simulations, the Grand Tack Hypothesis proposes how a great migration of Jupiter and Saturn in our early solar system accounts for the many unique characteristics of the rocky inner planets. So with that, I will pass it over to Mr. Monti.
Okay, thanks, Anna. I'm going to share my screen now, so bear with me. Okay, so as Anna said, the topic is the Grand Tack Hypothesis. And, it's about the migration of Jupiter and Saturn in the early solar system. And it's a hypothesis that was first developed, I guess, in the early 2000s. And there was a cover article in May of 2016 in the Scientific American about this. And it was also covered in one of the episodes of the Nova Planets series. It was back in July of last year, the episode on Jupiter. So before we get started, I know that a lot of you are going to have a lot of questions, and you have a lot of astronomical backgrounds. So in order to finish the presentation, I would ask if you have any questions to just note them down, and I'll attempt to answer them at the end of the session. Emphasis on the word attempt. So,
and Ron, if the folks want to put the questions in the chat, we can kind of keep track of them and try and feed them to you at the end of the call as well.
Okay. So first, let's set the stage. 4.5 billion years ago, Jupiter was the first planet to form and formed beyond the ice line in the solar system. So the presence of large amounts of gas, dust, and ice allowed it to start forming sooner and become larger than the other planets. And for many years, the Nebular Hypothesis provided the most accepted explanation for the formation of Jupiter and the other planets. And the Nebular Hypothesis had been around for many years. Like, I was surprised to see who actually came up with this. And it actually started with Immanuel Kant, the philosopher. And but I doubt that it was in the same form back then as it is recently. In the 1990s, the Nebular Hypothesis began to unravel. And what is the Nebular Hypothesis? If you look at this chart here, you'll see the planets, they're at scale in size, but not in distance. And to the left, you'll see the 4 terrestrial planets. And then you'll see the ice line, the gas giants, and the 2 ice giants. So these are somewhat of a misnomer, the gas giants and the ice giants, because Jupiter and Saturn have ice and Uranus and Neptune have gas, but it's just a proportion of ice in Uranus and Neptune is much higher. But the Nebular Hypothesis states that the planets formed from gas, dust, and ice, and interior to the ice line, gas and ice were much less plentiful due to the ignition blast of the sun, followed by its heat and the solar wind. And it states that the planets remained in roughly the same orbits that they formed. So why is the nuclear hypothesis unraveling and being questioned? And there's 3 major sources for these questions. One is the updated research and observations of our own solar system. The second is observations of exoplanets and many other star systems. And the third is the increasingly sophisticated results from computer simulations on supercomputers. So let's take a look at each of these areas. The first area, the questions raised by the observations within our own solar system. The first question was when they were looking in our own solar system, and they're saying, according to our theories of celestial mechanics, and we look at where the asteroid belt is formed and how we think the initial cloud of our solar system formed, there should be a planet where the asteroid belt is, but we don't see one. And here you can see a little chart of where that is, between the asteroid belt between Jupiter and Mars. And then another question that they had was, how did the Earth acquire its water? I mean, if the water vapor and dust, a lot of the dust were, where the gas and ice were stripped away from the inner solar system, how did the Earth get its water? These are just a couple of the questions that the observations led to, but more particularly, I'm just taking the ones that apply to the Grand Tack. This is a really neat illustration here. It shows the water that's, if you took all the surface water on Earth and rolled it up into a sphere, it would be about 1,200 miles in diameter. And a lot of people think that it should be more than that, because the Earth is 2/3 covered by water. But if you, for instance, take a look at the Daily Planet globe down by the museum, that's 70 feet in diameter. At that same scale, the average depth of the oceans would be about 2/3 or 1/3 of an inch, which is really amazing. Okay, the second area where questions were raised is the observation of exoplanets. And if you take a look at some of the recent or somewhat recent exoplanet observations, exoplanets were first confirmed in the 1990s, but many more exoplanets were discovered after the launch of the Kepler and TESS space telescopes. And this is an illustration of the Kepler, which was active until 2018. And then this is TESS, which became active in 2018. And here's a chart that Jim used last month in his presentation, which was a very nice presentation. And here's our sun, and here's the center of our Milky Way galaxy, which is a barred spiral galaxy. And our sun is like just off the Orion spur here. And the Kepler was aiming its telescope into this cone-shaped area here within the between these two arms of the Milky Way. The TESS, a lot of people mistakenly assume that it's going to take in a larger area, but it's not. It's going to take in a smaller area, and it's going to actually find more exoplanets. But the real need for the TESS is not necessarily to find more exoplanets, but to learn more about these exoplanet systems. This is kind of a neat chart. This is the a 360-degree view of space around the Earth. And you can see here, this is the Milky Way that forms this U-shaped structure here. And each one of these little circles that you see here in the background is an exoplanet they discovered by the year 2019. And they had discovered 4,000 by then. And this little glob over here, those are the ones that the TESS observatory discovered. And this is another really cool chart. This is all the exoplanets that were discovered through the year 2015. And the TESS discoveries are in yellow, and the ground observatories found the ones in blue. So the x-axis along here is an exponential axis, and it's going from 1 to 10 to 100, as you can see. And this represents the orbital period in days. And that generally correlates well with the distance from the star, the distance of the planet to the star. And the y-axis is the planet radius shown in terms of Earth radiuses. So here, this first line across is Earth. Up here is 4, which is Neptune, and then 10, which is Jupiter. Now, on this chart, the Earth would be right about here. So that's 365-day orbital period in 1 Earth radius. Now, the first thing that's kind of apparent is that everything seems to be to the left and to the upper reaches of where the Earth is. And that's kind of logical, because anything above where the Earth is a larger planet, which is easier to observe. And anything to the left of the Earth is one that transits the star much faster than the Earth. So those are the ones that are most likely to be discovered. And that's why you see this chart here. And this just tells you a little bit about that. Now, when the astronomers began looking at this chart and their findings, they noticed there were some anomalies here with the Nebular Hypothesis. And in the upper left-hand corner it shows what appear to be very large planets orbiting in closer to the star than Earth is to the sun. Now, that seems to be an anomaly, because, in our solar system, there's no gas giant planets anywhere near the sun. So that was one question that came up in their minds. And here's an artist's illustration of what they call a hot Jupiter. It's in close to the sun, so they say it's hot, and it's the size of Jupiter. And then another area that caused a lot of questions was this area in here, which is it's about 1.5 to 2 times the size of the Earth, and it's in closer to the sun. And these are called super Earths. And this is an artist's illustration of Captain B, an exoplanet that was discovered, and its size compared to the Earth. So this is about 1.5 to 2 times the size of the Earth. And they found a lot of them in these exoplanetary systems. So now, what were some of the questions posed by looking at these exoplanet observations? The first one is, why isn't there any hot Jupiters in our solar system? And why aren't there any super Earths in our solar system? And then a third one is, can we see any planetary systems actually forming around other stars? And if so, can they explain the configuration of our solar system, and why is it different than these other ones? One early conclusion that they came to was that the gas giant planets could not have formed close to their stars because of Jupiter formed about 1 million years after the formation of the sun and the ignition of the sun. So the sun blew away most of the gas and ice that formed Jupiter. So the only thing that they could therefore conclude was that Jupiter in our solar system must have migrated to where it is today. Another thing that they found in doing these exoplanetary observations is that they actually found these photos. They have photos of these exoplanetary systems forming, and in there you can see the rings of where the gas and dust are, and the gaps where the planets are forming. As the planets form, they clear out a path in the gas, dust, and ice there. And this one is the planetary system is called HL Tauri, And this is an image from the ALMA radio telescope in Chile, in the Atacama Desert. And this is a picture of the ALMA radio telescope. It's really big. I mean, if you compared this to the large array in New Mexico, I think it would dwarf it. And if you ever have a chance to look up any information about it, it's very interesting. So now the third area that questions arose from was computer simulations. And these simulations require extremely complex programs and a lot of computing power. And much of this power became available in the last decade or two. So they put information from these exoplanetary systems into the simulation. And these simulations showed that planetary migration is indeed a very likely possibility. So what does a simulation look like? So this is 3 snapshots from a simulation showing an early solar system midway through the evolution, and then our solar system as it looks today. And the astronomers construct these models and run simulations covering billions of years to see if their models result in something like what we see today. So this is a yeah, so that was a pretty good demonstration of what a simulation might look like. And how are these simulations used? You know, what are some of the ground rules for them? Many beginning parameters of the simulated solar system can be varied significantly, such as where did Jupiter form? You know, like where was its initial location? Or what was the size and rotation of the original gas cloud that formed the solar system? And they'll run thousands of simulations and using many combinations of variables covering hundreds of millions of years. So even tiny changes in the initial parameters of the simulation can result in very different outcomes. It was kind of like the butterfly effect. But the results tend to fall into numerous complex patterns which can be expressed as probabilities. And the probabilities are matched against what we see in our own solar system and other exosystems to develop hypotheses about the evolution of planetary systems. So this is not a graph of the solar system. It's just a three-dimensional graph that I'm using as an example. But as they run these simulations, they may, for instance, be looking at, well, where did Mars form, and in what, how far from the sun? And they'll each one of these dots that form here will give the result of one of the simulations. And they'll say, okay, it looks like there's about 50% chance that it'll form in this group here in the middle. But there's also like 25% up here and another 25% down here. And those other amounts, you can't just look at the middle one and pick out the most likely one and say, well, that's it. No, with these models, anything that's possible can happen. So you have to be very careful about the conclusions that you draw. So whenever I talk about, chaotic or read about chaotic systems, I go back to the time that I attended this lecture at Wake Tech, and it was by Neil Colemans, who's a professor at the University of Maine, and he wrote one of my favorite books. It was What If the Moon Didn't Exist? And I just stumbled upon this talk that was going to be given, and I made sure I got there. And he gave a great talk, and I'm going to go over that in a minute. But he has written a series of astronomy textbooks. It's probably now in their 8th or 9th editions. And I just want to read to you something that came from that to just give you an idea of what happens, how unlikely it is that our solar system, turned out the way it is. And so he starts out saying that, our solar system was formed from a cloud that was formed by a supernova. And that cloud, there was a second supernova that went off, and the shock wave from the second supernova collapsed the cloud from the first. It caused a gravitational attraction, greater gravitational attraction between the particles and dust in the first cloud. And as it started collapsing, he describes what's going on. And this is what he says. This is from the book, the introduction to the book. The cloud collapse was extremely chaotic. We now know that small changes in the motion and mass of the supernova remnant and in the cloud that formed from it could have led to extremely different physical conditions in the collapsing gas and dust cloud. Even a microscopic change in the initial motion of the interstellar matter that formed the solar system could have led to many of the changes described in this book. This extreme sensitivity of matter to tiny changes explains why weather predicting will never be an exact science. Analogously, by making small changes in the collapsing, swirling cloud that became our solar system, it is entirely plausible that the planets, moons, and other matter here would all be different than they are. For example, if the initial cloudlet had slightly less rotation than it did, the sun would be more massive than it is. The planets would also have different masses, chemical compositions, and perhaps different locations. Other changes in the collapsing cloud would have led to the Earth having a different mass or spinning on its axis at a different angle as it orbits the sun. The Earth's global properties, such as its mass, chemical composition, and rotation rate, could all have been different. And since the laws of nature and chemistry would have allowed matter to be distributed differently following the formation of our solar system. So, when you start learning more about this, you have to say, when they say that it's highly unlikely that our solar system formed the way it did, it is, because there's so many variables that you have to take into account. So some of the questions that were raised by these computer simulations are, why is Mars so small compared with Venus and the Earth? Here you can see Mars, its diameter is about half that of Earth, but its mass is only 10% that of Earth. Venus is about the same size as Earth. And Mercury is smaller, but there was some impact, some impacts that changed the way that it evolved in the solar system. So the next one is, this is something that they got by running some of their simulations. And in this, one of these simulations, or some of them, Venus was the closest planet, then Earth, then a mega Mars, which is as large as Earth. And then you had in the asteroid belt, you had Marses, planets that were as large as Mars, along with smaller planetesimals, and then Jupiter. You know, and then you compare that to what we have in our solar system now. It's very different. So another question was, why are there such unique orbital eccentricities and inclinations in our current solar system? You know, and if you look at the axes in rotation of our solar system, you can see that some of these are very different, especially as you get farther out with the solar system. And Uranus, you know, is actually spinning on its side. This is a clip from the NOVA Planet series that aired last July of 2020, and it's really good. And I'm gonna play for you now. If for some reason it doesn't show, if you want to take a screenshot of this, and you can go to this website and watch it there. And I'm just going to be showing about 7 minutes, starting at 23:30.
Hey, Ron, nothing. We're just seeing a fixed slide. We're not seeing a video.
Oh, okay. I might have to try something else here.
There you go.
Okay. Can you hear that?
No.
You might need to share sound up in the top of the Zoom window. You can share your sound under the where it shows you're sharing your screen.
Oh. Where was that again?
If you look up where it said, where if you like go to the top of your screen, this is on my computer anyway, it'll show like the screen share that you're sharing your screen. And if you click on one of the little arrows, it'll let you share sound.
There might also be a way, Ron, when if you stop sharing and then start again, there is an option to enable or optimize for sharing video and sound. You have to check those boxes.
Yeah, okay.
Or I just put the link showing what the menu is in the chat.
Okay. Oh, here it is. I found it.
Yeah, it's not intuitive, that's for sure.
Yeah. Yeah, see it and hear it now.
After
Yes.
marauding what would become the asteroid belt, Jupiter enters the region of space where Mars is forming. Continuing its journey, spiraling towards the sun. As Jupiter bulldozes inwards, its immense gravity scatters material in all directions. Some is sent careening into the sun. And some is thrown out into interstellar space.
It is because of the gravitational clearing of this neighborhood by Jupiter that Mars was unable to grow to more than 10% of that of the Earth. This is why Mars is small.
And by clearing material out of the inner solar system, the giant planet may also have prevented the formation of the super-Earths we see in other systems. And if it had continued moving inward, our planet too might never have formed. But then, just as it looks like Jupiter will sweep everything away, the giant planet stops in its tracks. Because in the far reaches of the outer solar system, another planet is forming. The solar system's second gas giant, Saturn. Its arrival changes everything.
As Jupiter moved inwards, Saturn moved inwards and caught up to Jupiter's orbit. When this happened, the two locked into a special configuration in a coherent manner. And now, locked as a unit, the two reversed their migration course and moved back out.
Saturn caused Jupiter to retreat. Leaving behind just enough material from which the inner planets could form. Mercury, Venus, and our home.
Earth is in exactly the right location to provide the environment for life to develop. So if Jupiter had moved around even more, who knows, maybe life never would have developed in the solar system as we know it.
And as its voyage across the solar system draws to a close, Jupiter helps to provide our living world with its most precious ingredient. Today, 2/3 of our planet's surface is covered by ocean. More than 320 million cubic miles of water. Each drop teeming with life.
One of the big questions about the evolution of our solar system is, how did we get water here on this planet?
So we think that the inner planets didn't naturally form with a lot of water. Water is primarily in the outer solar system. But if you end up having Jupiter and Saturn moving outwards, then that is able to suddenly deliver more water into the inner solar system.
So that was about a 7-minute clip. And that was about all they spoke about the Grand Tack in that episode of the planets. But there was a lot more to it. So the Grand Tack theory, this is a graph of what they believe happened, or they're hypothesizing what may have happened. This x-axis here is expressed in terms of astronomical units. And an astronomical unit, one astronomical unit is the distance of Earth to the sun today. So here you have the inner planets at about 1 astronomical unit. Here you have Jupiter and Saturn when they first formed. This is where they believe that those two planets formed. So they believe that Jupiter formed at 3.5 astronomical units from the sun, and then began migrating all the way into just 1.5 astronomical units. At the same time, or shortly thereafter, Saturn, which formed at 4.5 astronomical units, started migrating inward and moved into 2 astronomical units. 1.5 astronomical units is about where Mars is today. So then they both began migrating back outwards. And, as they said, they believe Saturn caused Jupiter to reverse course and come back out. So Jupiter turned around and came back out to 5.5 astronomical units, where it is today, and Saturn came back out to 7 AUs. And when they moved back out, they encountered Uranus and Neptune and kicked those planets back out farther into the solar system, which was another kind of anomaly that astronomers were trying to figure out. They were trying to figure out, why did Uranus and Neptune form so far from the sun? Well, this Grand Tack Hypothesis works together with another model called the Nice model that kind of works hand in hand, the two of those hypotheses. So this is the Grand Tack here, just covers these planets here, and the Nice model covers from Jupiter out to Neptune. But there was a big question left unanswered by the video. And when I saw the video, I said, how could you get something as big as Jupiter moving into the solar system to reverse course? I mean, look at the size of Jupiter compared to Earth. Earth is barely the size of the red spot there. You don't just use like battery power to change the orbit of Jupiter. So what happens is, it's all about the exchange of energy between Jupiter, Saturn, and the surrounding giant clouds of gas. And here's a little chart of Jupiter when it was first forming. And here you have the planet clearing out its orbital pathway, clearing out the dust and ice. Part of it accretes onto Jupiter, and part gets scattered outward and inward. There's more dense gas outside of Jupiter's orbit than inside. And what happens is, as Jupiter is clearing out its pathway, it exerts a force, a torquing force, against this denser cloud of gas here. And the net effect is that it pushes Jupiter away from the gas cloud outside the orbit. The inner gas cloud also pushes against Jupiter, but since it's less dense, the net effect of the two pushing is that Jupiter moves inward. And this is just a simulation when they ran some simulations of what that looked like. You can see these arms or arcs of gas and ice and dust extending from the planet into those gas clouds. And it illustrates how the material and the energy is being exchanged between Jupiter and those gas clouds. This is an illustration of what they believe the gas cloud looked like that formed our solar system. And if you'll notice, it's like teardrop shape with a narrow end towards the sun and the wider end out farther away from the sun. So now this is a slightly different chart of the same thing. And the x-axis is the distance to the sun, and the y-axis is the density of the gas clouds. So here you have Jupiter clearing out a pathway, and on the inside, you see how the gas cloud is getting denser and denser as it gets towards Jupiter. Then it drops way down because Jupiter's clearing it out. Then again, it picks up again towards the outer side of Jupiter, and it picks up and gets even denser on that side. And here you have the effect of the two torquing forces working on Jupiter and pushing it, the net effect pushing it in towards the sun. But Jupiter is not alone. Slightly after Jupiter formed, and Jupiter formed about 1 million years after the sun formed, Saturn began to form. And Saturn is out farther, and the gas clouds are even denser out there. So you can see the density of the cloud around Jupiter is higher, and on the outside of Jupiter, it's even higher yet. So what happens here is that you have the same net effect of the torquing forces working on Saturn that worked on Jupiter. But being smaller and with denser gas outside its orbit, Saturn moved faster and eventually caught up to Jupiter. So now here you see the effect of what's happening. As Saturn is moving inward, it's dissipating this cloud of gas, dust, and ice here between itself and Jupiter. So as Saturn catches up to Jupiter, it's clearing the gas in here. Now there's less dense gas on the outside of Jupiter's path than there is on the inside. So what happens is Jupiter stops and actually starts reversing course because of the torquing force against the inner cloud of gas and dust is pushing it back outward again. So now, in the video, the astrophysicist was talking about how they form a mean mass resonance between Jupiter and Saturn. And what happens in that is that their orbits synced up so that Jupiter made 3 orbits for 2 orbits of Saturn. And they kind of locked in that pattern. Once you lock into it, it's very difficult to break out of it because they reinforce one another. And what it's kind of like, this is not a great analogy, but it works. It's like a parent pushing a child on a swing, but instead of a parent and child, say the parent is planet A and the child is planet B. So when the child is coming backwards on the backward arc towards the parent, and it's slowing down and stopping, just a small push from the parent will cause a large reaction going in the other direction. And in this situation here, the energy is conserved. But if the parent pushes the child before the child is all the way back in that arc, the energy is dissipated, that the swing will almost come to a complete halt. So that's a rough analogy of what's happening in this mean mass resonance here. And what that means is the energy is being conserved, and the gas on this outer cloud now is still being attracted towards the sun, and it's going to pass by both Saturn and Jupiter And as the gas moves inward, the two planets pick up energy from the moving gas. There's like an exchange of energy between the gas and the two giant planets. As the gas moves inward, the density on the exterior of the orbit decreases, and Jupiter and Saturn continue migrating outward. So that's when they continued migrating outward to where they are today, and that's where they encountered, on the way, they encountered Uranus and Neptune. And that was enough to throw them out of that mean mass resonance, that synchronized orbits that they had. And it also threw Uranus and Neptune out into the farther reaches of the solar system. So how can the Grand Tack Hypothesis answer the questions that we raised earlier? Why isn't there a planet where the asteroid belt is located? Well, like I said in the video, when Jupiter started moving in, it scattered these asteroids and maybe even planetesimals all over the place. Some went inward towards the sun, some went out, someone out of the solar system completely. Why is Mars so small compared to the Earth and Venus? And how did Earth acquire its water? Well, this migration of Jupiter occurred before Mars formed. So it threw out a lot of the material from that area of the solar system that would have formed Mars. And there was actually more material there than was in the area of Earth and Venus. But it threw a lot of it away from the orbit of Mars. So how did the Earth acquire its water? Well, when Jupiter came inwards, it was dragging along a lot of asteroids and meteors that had attracted small planetesimals, maybe even small moons with it, and brought them and deposited them, a lot of them, into the inner solar system. Why aren't there any hot Jupiters in our solar system? Well, there were. Saturn formed shortly after Jupiter came in and caused Jupiter to reverse course and go back out again. And the last question was, why aren't there any super Earths in our solar system? And when Jupiter moved inward, it was flinging these asteroids and planetesimals inward. And some of them, there were already super Earths that were either already there or were going to have formed if it hadn't been for Jupiter. But anyway, some of these planets that were already there, these planetesimals that were flung inwards by Jupiter, they either crashed into these super Earths or they slingshot around. And if you watch any of the videos about how satellites pick up energy by slingshotting around the planet, the same thing was happening there. And when you slingshot around a planet with a satellite, the satellite picks up energy from the planet, and the planet loses energy to the satellite, but the planet is so huge in comparison that you can't even detect any difference. But if it's a lot of planetesimals and asteroids going in and they're all doing the same thing, it's going to bleed off the orbital energy from those super Earths, and they're going to start getting closer and closer to the sun and spiral inwards. And which is with a hypothesis. The hypothesis that that's what happened, is that those super Earths spiraled into the sun. Why is the Grand Tack a hypothesis rather than a theory? Because it's primarily based on stochastic computer models. And there's different kinds of models. Deterministic model, in deterministic models, the output of the model is fully determined by the values and the initial conditions. But in stochastic models, even those initial conditions have some inherent randomness. And I believe it's primarily because you can never establish with perfection what all of those initial conditions are. When you're dealing with things like the butterfly effect, where a small change in the early solar system can result in a great change later on, how are you going to model something like that? So if the Grand Tack is verified, it would explain why our solar system is so unlike the other stellar systems we had observed thus far. And in the next few years, the James Webb Space Telescope and other advanced enormous ground telescopes will come online and should help provide the evidence needed to verify or disprove the hypothesis. So there's like the Great Magellan Telescope and the extra large telescope and the 30-meter telescopes that are hopefully coming online in the near future that will help answer those questions. And so that's the presentation. If any of you have any questions, I'd be happy to try. Although I know some of you may have some zingers in here.
Hey, Ron. And
go ahead and let's everybody unmute and just ask questions. It's fine.
Hey, Ron, it's Doug Lively. Hey, how you doing? Great presentation, man. That's incredibly interesting. Just a real question is that as Saturn and Jupiter were kind of migrating out, did they actually kind of pull Mars out, or what's the idea of how did Mars get to where the early Jupiter would have been?
It formed after Jupiter and Saturn moved in and then moved back out again. So the material that was left there to form Mars, there was a lot less of it.
Ah. Okay, thanks.
Any other questions?
So, Ron, again, thanks. Sorry, can you hear me? Yeah,